Hello everyone, my name is Alan Carlos, and today we'll explore dry friction in our experiment called the Sleep Test Challenge. Friction is what keeps things from slipping and sliding too easily, like when your shoes scrape the floor or when brakes stop a car. But sometimes too much friction causes wear or energy loss. So let's find out how different materials behave. We will test two surfaces, a shoe on a paper and an eraser on a paper. First, we measure the force just because first we measure the force just before the object starts to move. That's the static friction force, also known as Fs. Then the force while it keeps sliding, that's the kinetic friction force, also known as Fk. So, the friction force of the shoe on the paper is 3.2 and the kinetic friction is 2.8. And also the eraser on paper, the friction force is 1.2. Then the kinetic friction force is 1. To find the coefficient of friction, we use the formulas of static friction force divided by the weight of an object. And also the kinetic friction force, we use kinetic friction force divided by the weight of an object. So the coefficient friction of static friction is 0.2 and the coefficient of kinetic friction is 0.28. And the eraser on the paper, the coefficient of static friction is 0.12. Also, the coefficient of kinetic friction is 0.10. In conclusion, the shoe on tile had the highest friction, perfect for grip and safety, and the eraser on paper had the least. Friction is essential to us. It helps machine grips, but too much friction can cause wear. Finding the right balance is key. And that's the end of activity 1. Hello everyone. So, our activity 2 is balancing act. Our topic is the centroid of plane areas. In this experiment, our goal is to find the centroid or the balance point of a flat shape. The centroid is very important to us because it helps us understand where the weight of an object acts. For example, when designing bridges, towers, or furnitures, knowing the centroid helps us make sure structures stay stable and balanced. So, let's imagine us having two cut papers of a shape of rectangle. Here is our shape. We split it into two rectangles. We will call rectangle A the vertical one, which is 3 centimeters wide and 4 centimeters tall. And the rectangle B is the horizontal one. It has 8 centimeters and 3 centimeters tall. First, the areas. We need to find the area first. The area of the rectangle A is 12 centimeters. And the rectangle B is 24 square meters. And the centroids. We need to find the centroids of rectangle A. So, rectangle A centroid is at 1 centimeters along X and 5 centimeters along Y. And the rectangle B centroid is at 4 centimeters along X and 1.5 centimeters along Y. Now, we will calculate the weighted sums for X, which is 12 times. Now, we calculate the weighted sums for X. So, 12 times 1.5 is 18. And 24 times 4 is 96. And we will add them together and we will get 114. For y, 12 times 5 equals 60 and 24 times 4 is 36. And add them together, we can get 96. And the next step is we need to divide the total area. So the x bar is 114 divided by 36, which is about 3.17 centimeters. And the y bar is 96 divided by 36, which is about 2.67 centimeters. So our analytical centroid is at 3.17 and 2.67 centimeters. Now, the easy experimental check is the hang shape one corner and draw a vertical line, hang it from another corner and draw the second line. Here we have is the first hang and the second hang. So the point where the line cross is the centroid. Here is the centroid. As you can see, it's around 3.2 centimeters along x and 2.7 centimeters along y. Very close to our calculations. Our computed centroid was 3.17 and 2.67, and our hanging test gave about 3.2 and 2.7. They match closely. The tiny difference comes from cutting and measuring. Both methods agree the math work. Why does this matter? We use centroid to place support and predict where loads act if a beam load isn't centered. It can tip or fail. This is the same idea scaled up to bridges and buildings. And this is the end of our activity 2. Hello everyone. This is our last experiment. We'll study the moment of inertia, which tells us how much an object resists rotating. In simple terms, heavier or wider shapes are harder to spin. We made two shapes from the same material. One is circle and one is thin strips. We poke a hole through each center and spin them using a pencil. The circle spins smoothly, while the strip wobbles and stops faster. The circle is more stable. So, we will compare the moments of inertia. We know the moments of inertia formula of a rectangle is BH cubic divided by 12. And the circle has pi r raised to 4 divided by 4. The moment of inertia of a circle is larger, so it resists change in motion better. Radius of gyration is showed how mass is spread from the axis. The circle was more stable because its mass was spread evenly. That's why wheels spin smoothly, while thin rods twist easily. We used the moments of inertia to design tables, rotating parts, and strong beams. And that is the end of our last experiment. Through this project, we realized statics is not just math. It's all around us. And we learn how friction affects safety and motion. And also we finding the centroid taught us how balance matter in design. And the moment of inertia showed us how shape affects stabilities. Teamwork helps us understand these concepts better because learning is easier when you experiment together. Thank you for watching.